Hi, we're now moving to all pairs shortest path algorithms, and these are still shortest path algorithms, but with Dijkstra or Bellman-Ford, we only find the shortest path from one vertex to every other one. Whereas now, we're going to find all the shortest path simultaneously. So for every pair of vertices in a graph, you can work out the shortest path between that pair, all in one go. Now, if you want to, you can apply Dijkstra or Bellman-Ford repeatedly to find all the shortest path. That is, you just start it off at different vertices. So if you have n vertices, you just run the algorithm n times. And this is actually something I asked you to think about a few lectures ago. I mean, if you know that you're going to find all the shortest path anyway, can you do something better? Because one way to look at it is, with Dijkstra or with Bellman-Ford, you have to check every single edge anyway, right? Meaning that if I find the shortest path from A to B, then I need to find the shortest path from B to A, I'll be looking at the same edges twice. So how can you improve on that? Well, first thing we do is we're going to change our recursion tree a little bit, because we basically changed our problem. So the recursion tree that we used earlier is suitable for single source shortest path, but because now we're going to look at all the shortest paths simultaneously, we're going to have a different decomposition. In fact, we're going to have two, because we are going to be discussing two different methods. One is called matrix multiplication, and the other one is called Floyd-Warshall. We're doing matrix multiplication now. And they do have different decompositions, but in the end, they're quite similar. So in the case of matrix multiplication, this is the main idea. If I have Pij as the shortest path from vertex xi to xj, then I can decompose that shortest path into Pik, which is the shortest path from xi to sk for some vertex xk, and the weight of the edge kj. Now, at first, this may look like a normal decomposition. In fact, isn't that what we did here anyway? Well, the catch is, we're going to say that Pij contains at most m edges. You see, with Dijkstra, you don't really care how many edges are in the shortest path, right? You don't really keep track of that. With Bellman-Ford, you kind of do indirectly because you run the loop phi-1 times. But now, in our decomposition, we're going to say that the shortest path here have at most m edges. So the subproblem must give me the shortest path with m-1 edges, because I take out one edge out. You may be wondering why we are doing this, and hopefully it'll be clear soon. But this is actually a dynamic programming algorithm. So we're actually just doing brute force here. And just as an aside, if you remember the 4 steps of dynamic programming, we're actually jumping to the second one now. Because can you show that there's an optimal substructure here? Yeah, there is. And I'm not going to go through that again because it's pretty much the same idea as before. Right? So now let's focus on the recursive relation. And I'm going to explain why we're doing the decomposition this way. And to do that, we're going to introduce a new notation here. We're going to say that Lijm is the weight of the shortest path from I to j with at most m edges. So the m there is not the power of L. It's just saying that you have at most m edges. Now, remember, Pij is the actual path. But we're not going to worry about the actual path. We're just going to worry about the weight of that path. And we're using Lijm to represent that. Maybe you can try to get used to the notation by thinking what Lij0 is. Well, this is the weight of the shortest path from I to j using at most 0 edges. Can you go anywhere with 0 edges? No, you can't. So the shortest path is going to be 0 if I is equal to j. You don't have to go anywhere. Or if I and j are not the same, then the shortest path is going to be infinity because you can't actually go there with 0 edges. Okay? Now let's increase I to 1. What do you think about Lij1? This is the weight of the shortest path if you're allowed to use at most one edge, only one edge. So what's that mean? Well, the shortest path between I and j, if you're only allowed to use one edge, is just the weight of the edge between I and j. That's it. Right? What about L2ij? Now, this probably requires a bit more thinking, so I'm going to draw it here. Let's say you're going from I to j, and you're allowed to use at most 2 edges. You can use just one, but you are also allowed to use more than one. You're allowed to use up to 2. So what do you do? Well, if I can go directly from I to j, then that is one possible path, and the weight of that path is just going to be wij, the weight of the edge between I and j. Alternatively, I can try to go to one of these nodes, and the weight of the path is going to be the weight of the path from I to that node plus the weight of the edge from that node to j. And this recursive relation is captured in this equation here. Note that we're going to say that the weight from j to j is just 0, just to make this work. Right, you see how we're looking at all the L1s to construct the L2. Maybe you can pause the video now and have a think about this, because this is a really crucial step for your understanding. Think about L3 and convince yourself that you need all the L2s to work it out. But you don't need the L1s to construct the L3, because L2 is the weight of the shortest path using at most 2 edges. So if the shorter path only requires 1 edge, then you go with that, right? So to be more general, we can say that to construct LM, I'm going to need all the LM minus 1s, as you can see in this recursive relation here. Now, one more time. These are the weights of the shortest path using up to m edges, not exactly m edges. So it could be the case that L3 is the same with L2, the same with L1, which is just the weight of the edge between I and j. That could be the case. If that is already the shortest path, then that's it. Also, if there are n vertices, then the shortest path should contain at most n minus 1 edges. We talked about this in a previous lecture as well, right? Because if you don't have n minus 1 edges, that means you have some sort of cycle in it. We're also going to assume that there are no negative cycles, because again, that will screw things up. So the shortest path must visit every vertex at most once and only once, right? Okay, so here's the approach that we're going to be doing. We're going to compute Li for all pairs of I and j. And I'm going to put that inside a matrix called, well, big L, I guess. Sorry, also using L here. We're going to be computing Lij1, Lij2, Lij3, and so on, for all the way up until L to the n minus 1. Why? Because as I said before, your shortest path should visit every vertex at most 1, so you will have n minus 1 edges in there. Right. So again, get used to the idea what the big L's are. Big L1 is just the adjacency matrix, because you're only allowed to use 1 edge. Big L2 is the weights of the shortest path if we use up to 2 edges. And this is a big matrix. Actually, I'll just show you what the matrix looks like. This is it, right? So here you got, you have 5 vertices, 1, 2, 3, 4, 5. And these, the matrix tells you the shortest distance between any 2 pairs. So between 1 and 5 is minus, well, this is the answer actually, L4, that's the answer. Between 1 and 5, the shortest distance is minus 4. Between 5 and 3, the shortest distance is minus 4, and so on. Okay, so as I mentioned before, this is actually a brute force approach with dynamic programming, because you won't be doing the same calculation again and again. But you're actually trying to work out every single path from I to j, well, sorry, I should say every single shortest path from I to j, with just 1 edge, and then 2 edges, and then 3 edges, and so on. And the trick here is that you can construct L2 from L1. You can construct L3 from L2. You can construct L5 from L4. You don't need L3, L2, L1, and the rest. You just need the previous L matrix. And you need the adjacency matrix, but we'll get into that, right? So that's a basic idea. Now, I think the best way to explain this algorithm is just to go through an example. So that's what we're going to do. We're going to use L1 here. We're going to use this graph as an example, and the answer is going to be L4 here. So we're going to start with L1, which is the adjacency matrix. And let's see how we compute L2. We're going to start with L1 to 2. So in the matrix, we're going to try to compute this cell here. I guess it doesn't really matter if I use big L or small l, because, well, they're kind of the same anyway. Sorry, I hope this is not confusing. Anyway, L1 to 2 is going to be the weight of the shortest path or just the shortest path, between 1 and 2 using at most 2 edges. So how do we compute that? Well, if we can use 2 different edges, then the first edge can be the edge going from 1 to 1. This one here, the edge going from 1 to 1. And the second one can be the edge going from 1 to 2. But we already computed L111. It's in the adjacency matrix here. So going from 1 to 1 is just going to cost you 0. Going from 1 to 2 is going to cost you 8. So the cost is going to be 8. But is that all? No, because we're actually going to find the shortest path. So what we have to do is we only check going from 1 to 1 and then from 1 to 2. What if we go from 1 to 2 and then 2 to 2? That's the second case here. And of course, this is kind of stupid because it's the same thing. Because, well, it's only 2 edges, so you can't really do much, right? Because L111 is just going to be 0, and weight to 2 is just going to be 0 as well. So really, these two are the same. But as I go further down, you can see what's going on with the algorithm here. I'm going to see if I can go from 1 to 3 in just one edge, right? And that is the value here. The answer I can't because infinity. And then look at the edge between 3 and 2, which is 7. So infinity plus 7 is going to be infinity. So nope. So basically what I'm doing here is I'm testing 2 different edges, right? And I'm looking at all possible combination of going from 1 to 2 using 2 different edges. So I try 1, 1, 2. I try 1, 2, 2. I try 1, 3, 2. I try 1, 4, 2. I try 1, 5, 2. And I worked out what is the shortest path for all of them. And then, how do I work out the shortest path? I just take the minimum, which is going to be 8. So hopefully you can see now why this is a brute force approach, because you're actually trying every combination, right? Let's try next one. I want to work out this one here. Now, this is going to be boring. Yeah, I have 5 lines here, and I'm doing a lot of work here. But if you think about it, this is we trying to find the shortest path from 1 to 3. Okay, and I'm going to try to go from 1 to 1 and then 1 to 3, 1 to 2 and then 2 to 3. But if you notice, if you look at the graph here, there is no way you can get to 1 to 3 using only 2 edges. So all of that is going to be infinity, right? Well, at least one side is going to be infinity. So I guess that is not an interesting example at all. We're going to move forward, I guess. Let's jump ahead. Let's try to do L3. We're going to go from L3 to L4. So before we were just doing L1 to L2, which, as I said, not that interesting because L1 just the adjacency matrix, so gonna be using the adjacency matrix twice here. But now if you want to go from L3 to L4, you need the adjacency matrix. So you need L3 and you also need L1, because you need L1 to work out all these weights, the W's. And you need L3 to work out the left hand side here, because these contain the shortest path with at most 3 edges that you have so far. Right, now we're gonna be computing L4. We're gonna start with the this cell again, the first one. Sorry, I'm in the second cell here because the diagonal is always going to be 0, so we want to compute the first cell here. Now, we want to work out L1 to 4, which is the shortest path from 1 to 2, with using at most 4 edges. Hopefully you can see that the answer is actually, what's the answer? What's the lowest you can go from 1 to 2? So I can go -4, 1, -5, and then 7. So that's -9 plus 8. It's going to be -1. So definitely better than the 2 that we have right now. So if you only use 3 edges, then I think 8 is the best one that you can do. So yeah, well, you only need 1 edge to get 8. Right, so using up to 3 edges, the best one you can do is still just 8. Now, we're going to try to improve that. How we do it? All right, let's say, so we want to go from 1 to 2, right? Okay, let's go from 1 to 1 and then from 1 to 2. That's the first line here. Okay, so the weight of the path with at most 3 edges going from 1 to 1 is just going to be 0. and the weight from 1 to 2, this is from the adjacency matrix, is 8. So the path is going to be 8. Same with 1, 2, and then 2, 2. Now, 1, 3, 3, 2, that's when we're actually doing something. The path going from 1 to 3, the shortest path going from 1 to 3, using at most 3 edges is actually minus 8. And you can see it here, right? 1, 5, 4, 3 is minus 8. The weight of the edge going from 3 to 2 is 7. So now I can go from 1 to 2 with minus 8 plus 7 equal to minus 1. So you're going to modify this into minus 1. Well, the rest is just going to be infinity because, well, this one here, you can't go from 4 to 2, so who cares? And the last one, you can't go from 5 to 2, so again, it's not going to do anything. But we at least modify the first cell to be minus 1. So that is how the algorithm works. And I hope you can see why this is brute force. You're actually trying every single combination. And you can double check this on your own. It's actually very long and very tedious. I don't think I'm going to be that evil to ask you to do this in the exam, or even if I do, it's going to be small. Like even 5 by 5 can take quite a bit of time because you are doing a lot of operations. But this is the answer here. You can run this, you can do the calculations to see if you get the same answer. At least most of the time, you don't have to really change the values because sometimes the edge doesn't do anything. When you try to relax something, it doesn't do much. So it's not as bad as doing a lot of like matrix multiplication. And actually, that's the next point I want to get to. When we talk about the complexity of this algorithm, do you remember how to do matrix multiplication? If I want to compute L3 times W as two different matrices, how do you do that? Well, to get the cell 1, 2, you will have to do these calculations, right? You have to do 0, 8, minus 8, minus 3, minus 4 times 8, 0, 7, infinity, infinity. So you're going to multiply the first element, the first column with the first row here, the second column with the second row, third column with the third row, and so on. This is what you're going to be doing. So you're doing 5 multiplications and 4 additions, or just say you're doing n multiplication and n additions there. If you have two matrices of size n each, then the complexity of multiplying the two matrices is going to be n cubed. Now, what are we doing with this matrix multiplication method? Well, this is why it's called matrix multiplication method. Look at what we're doing. We're looking at 0 and 8, and then 8 and 0, 8 and 7, 3 and infinity, and minus 1 infinity. So you see the similarity here? Sorry, I meant to say minus 3 and minus 4, not 3 and 1. I don't know what happened. Anyway, yeah, do you see the similarity? Well, instead of doing multiply, we're doing addition here. And also, instead of doing a bunch of additions, we're actually finding the minimum. But really, it's the same number of operations. So matrix multiplication is n cubed because, well, multiplication is n squared. And you're doing n squared multiplications, basically. So that's n cubed. Now, when it comes to this algorithm here, complexity is also phi cubed. Well, phi is the number of vertices you have in the graph. So that's the dimension of the matrix. So if you go from Li plus 1 to Li, it's like the same as doing one matrix multiplication. Sorry, if you go from Li to Li plus 1, you are doing one multiplication. So that is phi times phi cubed. That's phi to the 4. Now you can ask yourself, how does this compare to Bellman-Ford or Dijkstra repeatedly? If you remember Bellman-Ford, Bellman-Ford is actually phi cubed. So now if you look at, well, not phi cubed exactly, but it's phi times e. But I said that e can be up to phi squared. So roughly phi cubed. So this is just phi to the 4. And Dijkstra is even cheaper, but well, Dijkstra can't handle negative weights, whereas this one can. So would be a bit unfair to compare it. So yeah, it doesn't seem too appealing to see that this is only phi to the 4, which is the same as doing Bellman-Ford repeatedly. But you can improve the running time significantly by using repeated squarings. So what do I mean by repeated squarings? Well, let's say you want to compute x to the power of n. Are you going to do n multiplications? Well, you won't. For example, if I want to do x to the 19, I'll be doing x squared, and then from there I'll square to get x to the 4, then I'll square to get x to the 8 and x to the 16, and from there I can just do times x squared times x, I'll get x to the 19. You're not going to be doing 19 multiplications, correct? And you can do the same trick with matrix multiplications. So you can also do the same trick with this method. Now I'm going to use the multiply symbol here because I guess I don't have anything better to use. But with this method, you realize that L1 is just the adjacency matrix W. Sorry, I don't think I defined this earlier, but let's say that W is the adjacency matrix. Right. If you want to compute L2, you're going to combine somehow. Well, I guess you're going to use L1 together with the adjacency matrix to get L2. And to get L3, you're just going to do L2 times W, say, right? This is what L3 is. But then I can just jump straight to L4. I don't need to compute L3. Why? Because if L4 is L3 times W, then this is just L2 times W. And because this is just like you applying W twice, you can just square them. And this is what it is. That's what L4 is. W squared times W squared. So again, with L8, it's just going to be L4 times L4. You can expand it like that. This is just going to be W to the 8. W4. So really, with this method, all you need to have is W. And you keep on squaring it in a way. Well, not really squaring it because this is not really multiplication. This is the operation that we talked about before, right? And so if you need to compute L to 19, you just jump from L1 to L2 to L4, L8 to L16, and then you just multiply by W and W squared, just as we did before with multiplications. Okay, so actually, the complexity of this algorithm is not phi to the 4, is phi cubed log phi. Because instead of doing multiplication, well, sorry, I keep saying multiplication and process, but instead of doing process phi times, you only need to do log phi times because of this trick. You can do even better if you use something called Strasson's algorithm. This is like Karasuba algorithm for matrix multiplication. So you can do that in v to the 2.807 log phi. You can also use other fast multiplication tricks. So at the very least, we can say this is phi cubed log phi. Okay. And finally, don't forget that this is a dynamic programming method. So we're actually doing brute force. And make sure you understand why this is brute force. So in terms of correctness, I guess it's not that interesting because we are trying every single path. So yeah, I think that's all we need to talk about in terms of correctness. You can consult the textbook to see more. If you're not convinced, you can look at it more. But for this unit, as long as you understand how it works, you understand the complexity and why it's like that, and you understand why it's correct because it's brute force, so you can see why it's brute force, that should be enough. I do have one implementation here for it. I wrote this last year. I think this is what I used to generate the example. So hopefully it's still okay. You can give it a try and let me know if it doesn't work. I don't think I'll be asking you code questions during the exam because I believe that code is something that you do when you're typing, not when you're writing code. But I may ask you something similar to the submission. So I'll give you a code which is faulty and you have to identify where the fault is. So this is why I'm giving you the code here. Okay, so that is it for this method. I'm gonna come back soon with the last method for this week, the flight washer one. Right, see you then.